So today we're going to explore creating asynchronous or ripple counters with non-natural mod numbers. So up until now, we've done ripple counters with natural mod numbers, which are powers of 2. So the modulus is either 4 or 8 or 16, and so forth. But what if we want to create a modulus counter that is not a natural power of 2? So let's say mod 9 in this example. So how do we do that? Okay, first thing is 9 in base 10, decimal base 10, is equal to 1001 in base 2 in binary. So I need 4 bits to represent 9 in binary. So that means in the type of counters we're doing, I need 4 flip-flops because each Q output represents a single bit. Furthermore, I am going to assign, my naming convention is that I'm going to call the most significant bit, Q is going to be the output Q3, then Q2, then Q1, and the least significant bit I'm going to represent by the output Q0. All right, so how do I go about drawing a schematic for this? So I'm going to start as if I'm making a regular 2 to the 4 or mod 16 counter. So I'm going to have 4 flip-flops, and we'll use JK flip-flops wired in toggle mode. I'm going to make them negative edge triggered. That's what this little bubble is for. I'm going to have Q and Q bar. I don't really need the Q bar, but I'll put it there anyway. Then I'm going to have my asynchronous input. So sometimes these are called pre, and sometimes they are called R or S. And actually the one at the top is usually set, meaning it makes Q equal to 1. And it's asynchronous because you can set Q equal to 1 at any point in the clock cycle. And over at the bottom, I have the reset, which makes Q 0 at any point in the clock cycle. And the active low comes into this because it will only set or reset when the asynchronous input is pulsed low momentarily. So to keep it inactive, I want to keep my asynchronous inputs high. And to wire my flip-flops in toggle mode, I want J equal to K equal to logic high. So I'm going to wire those guys to VCC. So let's just go ahead and copy and paste this. So I'm going to need 4 of them. Over here, and the third one over here, and the fourth one over here. And furthermore, I'm gonna take the Q outputs as my counter outputs. So I'm gonna call this Q0. Now, why, when I have Q3 is my least significant bit, it's my most significant bit, and I always keep my most significant bit over on the left. So why am I putting my Q0 over here on the left in my schematic? And the reason I'm doing that is just because the wiring is greatly simplified if I do that. Why? Because I am also going to wire the output Q to the clock of the next stage. So my wiring just looks neater if I do it this way, but you don't have to. You can rearrange the flip-flops such that you have Q3, which is the most significant bit, over on the left visually. But the only thing you have to be careful about is that they are wired in the proper manner. So the system clock, which is basically just a 50% duty cycle square wave, that has to go into the flip-flop that's Q0. And the frequency of Q0 is going to be half the clock frequency. And at every stage, the frequency is going to be halved. So the frequency of Q1 over here is going to be half the frequency of Q0, and the frequency of Q2 over here is going to be half the frequency of Q1, and the frequency of Q3 over here is going to be, again, half the frequency of Q2. So at every stage, I'm having the frequency. So by the time I get to Q3, I have already halved the clock frequency 4 times. 1, 2, 3, 4. So that means that Q3 is going to be at a frequency equal to the frequency of the clock divided by 2 to the 4. And let's just write that out because that seems like an important point. And I'll call it F3 because it's the frequency of Q3. And it's going to be equal to the frequency of the clock divided by 2 to the 4, which is 16. Okay. And furthermore, I'm going to make the assumption that the frequency of the clock is long enough to account for the propagation delay of each of the flip-flops. So each flip-flop has a certain propagation delay, meaning that the output Q is going to react after a certain finite amount of time after the clock pulse. And I'm going to assume that this is short enough that it is not going to significantly affect the operation of my counter. Okay, so let's finish wiring up our counter. So if I were wiring this to be a mod 16 counter, I would wire S bar and R bar all to VCC. But I'm not going to do that for my non-natural mod counter. I am only going to wire S bar to VCC. So let's do that. Do it that way. And so far this looks pretty good. And if I did the same to my R bar, then I would have a mod 16 counter. It would be an up counter, which I will prove to you later with the timing diagram. But I'm not going to do that. I'm going to do something different. So my strategy is going to be that I am going to count from 0 all the way to 8. And then when I reach 9 at the next clock pulse, I am only momentarily going to stay at 9. And then I'm going to asynchronously reset all my flip-flops back to 0. So how am I going to do that? What I'm going to do is I'm going to put a NAND gate over here. And the inputs to the NAND gate are just going to be the Q values that are high in the first invalid state. And the first invalid state is 1001. So as soon as I get to state 9, I want to asynchronously reset. So I am going to make a NAND gate whose inputs are Q3 and Q0. And as soon as Q3 and Q0 are both high, and only when Q3 and Q0 are both high, the output of the NAND gate will go low. It'll pulse low. It's going to reset all the flip-flops. So it's going to reset the counter output. So it'll all be 0. And we're just going to resume counting again. So under all other conditions, the NAND gate should be high, right? Let's draw the truth table for that. So I have Q3, Q0. In fact, let's draw the truth table with all values of Q. So I have Q3, Q2, Q1, Q0, and then I have the NAND gate output. And I have 16 possible rows in my truth table. Okay, so I've spared you the drawing of the truth table, and this is what I end up with. So here are my 16 possible permutations of Q3, Q2, Q1, Q0, and I've also written the state in decimal right next to it over here. And as you can see, looking at this NAND gate over here, the inputs are Q3 and Q1, and I know from the properties of a NAND gate that is going to be high, the output is going to be high, unless and only if Q3 and Q0 are both high, then it'll be low. So I'm going to look for all conditions in my truth table here where Q3 and Q0 are both high at the same time. And I know that under those conditions, my NAND gate is going to be low. And under all other conditions, it will be high. The effect of this is going to be that until I reach this first invalid state right over here, my NAND gate output is going to be high. And my counter will count normally. And at every clock edge, it will increase the sequence. It will increment by 1. And then what happens once it gets to 9? The NAND gate is going to go low. And that is going to have the effect of clearing the counter. It's going to make all the Qs reset back to 0. And once that happens, the NAND gate is going to go high again, and we will resume our count. Now, as we know, it's also possible for my counter to boot up in any random state that's valid. So I can boot up in any one of these states. And if I do that, well, it really depends which state I boot up in. So if I boot up in state 10, the NAND gate is high. At the next clock pulse, I will reach this state, 11, and the NAND gate will, again, go low. It will clear the counter back to this state. NAND gate will go high again, and I will resume my counting sequence. And we're going to write that out in a state transition diagram. So let's do that. So here I have the beginnings of a state transition diagram for a mod 9 ripple counter. And you will have noticed that I put all the possible states, even though it's mod 9. So really, I only want to be counting from 0 to 8. But it is possible for my flip-flops to be any state, any allowed state. So I can boot up in state 10 or 11. And that is valid. So I have to account for that. So let's see what happens. So I know that if I'm in state 0, I will progress to state 1. Now, remember that the states are inside the bubbles, and the arrows represent transitions at the clock edge. So these are synchronous transitions. So at the next clock edge, that's what these arrows mean, I'm going to increment my counter by 1. And the same thing, in fact, is going to happen between states 8 and 9. At the next clock edge, I will increment my counter, but then what happens? This NAND gate here is going to kick in because Q3 and Q0 are both high, and it's going to reset the counter state asynchronously back to 0. And we're going to draw the timing diagram, but we'll do that in a bit. So for now, I'm going to represent that asynchronous transition back to 0 with this dashed line. Because remember that my solid lines with the arrows represent synchronous transitions at the clock edge. Okay, but this is not a synchronous transition. This is an asynchronous transition caused by my NAND gate briefly becoming low, resetting all the flip-flops, and making the outputs, the Q outputs, equal to 0, which has the effect of clearing the counter. Okay, what happens though? Because remember I said I could boot up in any possible state. So what happens if I boot up in this state, 1010? Well, in fact, that NAND gate, as I can see here from my truth table, in state 10, my NAND gate is still going to be high. So at the next clock pulse, I'm going to progress to state 11. But oh, look what happens in state 11. Q3 and Q0 are both high. That's going to trigger that NAND gate action again. And it's going to trigger that asynchronous reset. And it's going to cause the counter state to go back to 0. And because it happens asynchronously again, that's why I have this dashed line. It's represented by the dashed line on the state transition diagram. What happens over here in state 1100? NAND gate is still high. So that's right over here. And the NAND gate is high. And as long as the NAND gate is high, that means I'm still in synchronous operation. So at the next clock edge, I will increment the counter sequence to 1101, Q3 and Q0 both high. And I'm going to asynchronously reset my counter. And same thing over here. If I boot up in state 14, then at the next clock edge, I will progress. I will increment to state 15 and then asynchronously reset back to 0. That's just the operation of the AND gate. In actual fact, I don't really care what happens after state 9 because I assume that these other invalid states are only going to occur on boot up. So as long as I have a valid path from any of these invalid states back into the valid counting sequence, which is this, then it really shouldn't matter. We'll see that more with synchronous counters. But for now, it's important to understand what happens when I boot up in an invalid state or I power on the counter. Okay, so let's draw the timing diagram for this. So to recap, what do we have? At a mod 9 ripple counter that is using asynchronous reset, and the logic circuit that I'm using to reset my counter once I reach the first invalid state is just this NAND gate here. Okay, so let's go ahead and draw the timing diagram. So I've got my clock input, and I really only want to show, let's say 9 or 10 clock cycles. And furthermore, I know that because I have negative edge triggered flip-flops, exciting things happen here in the negative edge. So I'm going to make my little arrows on the negative edge of the clock. All right, Q0, Q1, Q2, and Q3. And do you know what else I'm going to show? We're going to show the output of the NAND gate, which is going to be high until Q3 and Q0 are both high. So what's going to happen here? Now again, when I'm drawing these diagrams, I can choose to start arbitrarily at any point in the sequence that I want. And I'm going to choose, just because it seems easier, I'm going to choose to start when Q0 and Q1 and Q2 and Q3 are all 0. In other words, I'm going to choose to start in state 0, but that is my choice. And this NAND gate here is high. So Q0, I know, is going to toggle at the negative edge of the clock over here. That's this. And I don't want to do too many of these because I want to show you what happens when I reach state 9. So Q1 is going to toggle at the negative edge of Q0. So I'm going to draw arrows here. And now notice that I'm not showing propagation delay over here. I'm assuming that propagation delay is negligible compared to the total clock period. That's just going to simplify things for me. But in fact, I am going to have to take it into account. And it is one of the reasons why ripple counters are not ideal. So let's go high over here. What happens to Q2? So Q2's clock is Q1. So Q2 is going to stay 0 until negative edge of the clock over here. And then I will show Q1 going low. And here I'll show Q2 going low. And since Q2 is the clock for Q3, I'm going to put a little arrow at the falling edge of Q2. And then what's going to happen over here? Q3 is going to go high. I can actually continue my diagram a little bit longer for another clock cycle or two to see what happens. Actually, I didn't need to do so many here. So over here at the NAND gate. So the NAND gate stays high up until this point over here where Q0 is high and Q3 is high. And that is going to trigger the NAND gate output to go momentarily low, just until it has had sufficient time to clear the counter and all of the Qs, Q3 to Q0, have gone low. So let's show what happens. So the NAND gate goes low over here. Why is it going low? It's going low because Q3 is high and Q0 is high. And then what happens? As soon as the NAND gate output goes low, flip-flops reset. So Q3 is going to go low. Q2 is going to stay low. Q1 is going to stay low. And Q0 is going to have this weird little glitch where it went high, triggered the NAND gate, and got reset. So it's going to have this little glitch over here. Now, as soon as I get to this point where all Q outputs are now low again, my NAND gate has no reason to stay low. It's going to go back high. This weird thing. So I have this weird little glitch over here. Now let's look at my count sequence. So over here, I've got 0, 0, 0, 0. And then over here, I've got 0, 0, 0, 1. What do I have? 0, 0, 1, 0. So remember that when I take my counter output, I have to consider Q3 as my most significant bit. So that's the one on the left over here, and Q0 is this one over here. So when Q0 is low, it's a 0. When Q0 is high, it'll be a 1, like here. And over here, again, let's look at the counter output. I have 0, 0, 1, 1. So that's 0, 0, 1, 1. Continuing, I have 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1. And here I get to state 8, 1, 0, 0, 0. And then what happens? Well, ignoring these very odd looking glitches over here, if I move past them, I see that I'm right back again at state 0, 0, 0, 0. And I will resume the counting sequence as usual from there. But of course, I do have these odd looking glitches. So it doesn't matter so much that I have a little glitch here at the NAND gate, but this weird glitch here where Q0 momentarily goes high and then goes back low. Well, that can really have an effect if I'm taking the counter output as the input to another circuit, and it's less than ideal. And this is just one of the properties that makes ripple counters less than ideal. So the other, of course, is that the propagation delay is cumulative. So if I go back to look at my schematic, I can see that, first of all, from its very name, I know that it is asynchronous, and I can see that from the schematic because not all the clocks are clocked by the same signal. In fact, only Q0 is clocked by the system clock, and then the remaining flip-flops are clocked by the Q outputs of the previous stage. And I know that by the time I output Q3, Q3 is delayed with respect to the clock by 4 times the propagation delay of a single flip-flop. And at high frequencies, this can really make a difference. So we'll explore different ways to mitigate it with synchronous counters. I make is we said over here that the frequency of this flip-flop over here, so it's the fourth flip-flop that we've called Q3, and we've said that its frequency is simply the frequency of the clock over here divided by 2 to the 4, which would be the mod number if it were a natural mod counter. But it's not a natural mod counter. And does this equation still hold true even with a mod 9 counter like we created now? So let's go take a look at the timing diagram and see. So what do we have? So we have, I think we can agree that the frequency of Q0 is still half the frequency of the clock. And the frequency of Q1, we can say, is also still half the frequency of Q0. And Q2, I think we can, we can pretty much agree that it's also half the frequency of Q1. But look what happens over here to Q3. So first of all, one thing I can notice is this is definitely not a 50% duty cycle signal. And in general, we can say that non-natural mod counters will not necessarily have 50% duty cycle outputs. And the other thing we can say about it is actually the frequency is not half of Q2. It's something slightly different. And we're going to generalize this point. So let's write our new formula over here. So I'm going to erase this one over here. And I'm going to say that in general, the output frequency, and by output frequency, I mean the frequency of the last flip-flop. So the Q output of the last flip-flop. So that would be this guy over here, just to be clear. Okay, so the output frequency is going to be the frequency of the clock divided by the mod number. Now, this formula holds true for natural and non-natural counters. So you can use this formula across the board. And the duty cycle, so again, keep in mind that the duty cycle for a non-natural mod number counter is not going to be 50% necessarily. So actually, you can see that if you write out the count sequence. So in a mod 9 counter, basically, I am over in these first 9 rows from 0 to 8. And I can see that while in fact Q0 does toggle at every clock pulse, and Q1 here does seem to have a 50% duty cycle, right? It's 0, 0, and then it's 1, 1, then 0, 0 again. But if I look over here at Q3, I could see that in fact it's low for 7 clock pulses and high for only 1. So its duty cycle is going to be 1 over 9 expressed as a percentage, because out of 9 clock cycles, it's only ever high for one of them. And its frequency is going to be whatever the frequency of the clock is divided by 9.